Questions number 9, 10, 11, and 12 from the Unit 8 Quadrilateral Exam Review. Question number 9, we are given that the ABCD shape we see below is in fact a parallelogram. We are asked to solve for X, Y, and Z. Okay, right off the bat, looking at our shape, we know from a parallelogram that opposite sides are in fact congruent, meaning that we can set up the relationship between this side AD and side BC, and we can set up a relationship between side AB and CD. The one that is useful here is that 5z plus 5 is equal to 45. Setting up a two-step equation we can solve, we'll subtract 5 and then divide by 5, giving us that z is equal to 8. Okay, next property of a parallelogram that is useful is that opposite angles in a parallelogram are congruent, meaning we can set up a relationship between angle DAB and DCB, and we can set up a relationship between ABC and ADC. In this case, we'll use angle DAB and DCB because we know they're equal, giving us that 6y plus 8 is equal to 120. So to set up a two-step equation, we'll subtract 6 and divide by 6, giving us that y is equal to 19. The last relationship we are going to use from a parallelogram is that consecutive angles, so angle B here and angle C, if I were to add them together, they'd be 180. If I were to add angle A and angle B together, they would equal to 180. So consecutive sides are supplementary or add to 180 degrees, giving us that 3x plus 9 plus 120 degrees equals 180 degrees. So therefore, we can combine like terms, giving us 3x plus 129 equals 180. Setting up a two-step equation, we'll subtract 129 and divide by 3, giving us that x is equal to 17. Number 10, we are once again given a parallelogram and asked to solve for x, y, and z. The first relationship we're going to use in a parallelogram we could see is that once again opposite sides are congruent. Setting up the relationship, 4z plus 9 is equal to 61. Setting up a two-step equation that we can go ahead and solve, giving us that z is equal to 13. Now, the relationship between the diagonals in a parallelogram is that diagonals bisect each other. So that means that this piece is congruent to this piece, and this piece is congruent to this piece, giving us that 2y plus 1 is equal to 21, and 5x plus 9 is equal to 29. Two-step equations we can solve, giving us that y is equal to 10 and x is equal to 4. Question number 11 and 12, we should see that we're actually given a parallelogram, but this is a more specific parallelogram, and that it is a rhombus in each of these. So with the rhombus, we add a few more properties to the ones we know from a parallelogram. Opposite sides are congruent, diagonals bisect each other, or we get a little bit more specific. So we will go ahead and start with the fact that we know the diagonals bisect each other, meaning that 5x plus 4 is equal to 19, and 3y is equal to 21. Two and one-step equation we can solve. Subtract 4, divide by 5, giving us x is equal to 3. Divide by 3, giving us y is equal to 7. Now, to find angle Z, we're going to take a little bit more careful look at this section of the rhombus. And as you can see, if I take a look at the shape I've shaded in, that's a triangle. And more specifically, we know that the diagonals not only bisect, but they are perpendicular to each other. And the diagonals bisect opposite angles. Meaning that if I take a look at that diagram, we have a 90 degrees at all the intersections of the diagonal, so they are all perpendicular. But additionally, if this angle is 68, that also means that this angle is 68 degrees, meaning that I have now set up a triangle sum theorem scenario where z plus 90 plus 68 should be equal to 180 degrees. So we'll combine like terms and solve, giving us that z is equal to 22 degrees. Okay, problem number 12 is also a rhombus. So all the properties we had used in problem number 11 will be useful. That opposite sides are congruent, meaning 13x minus 11 equals 54. This is a two-step equation which we can solve, giving us that x is equal to 5. The next relationship we're going to use is the fact that opposite angles are congruent, but also the diagonals bisect our angles, giving us that if we're looking for y in our diagram, if this angle is 54, that means that this angle is 54. And if this whole angle is congruent to this whole angle, that means that this piece is congruent to this piece, and this half is congruent to this half, giving us that y is equal to 54. Now, this same idea of diagonals bisecting is going to be helpful for as we take a look at z, is that if this is z degrees, that means that this is also z degrees. And if we know that the diagonals are perpendicular, that means that all of these are right angles, which means that looking at very similar to what we had before, we have a triangle sum theorem happening in our triangle that I've outlined in green here. Z plus 90 plus 54 should equal 180, or that z is equal to 36 degrees. Note in both of these two problems, we use properties of a rhombus to help us set up an old favorite, the triangle sum theorem, which happened to reoccur because we had right angles in our shape. Not so much in parallelograms, we didn't have that diagonals being perpendicular there, but the properties themselves were fine.